So today we continue working with radicals, and then we're going to change gears and talk about products of binomials. I think it'll be something you've seen before, and it should be pretty straightforward. And that's going to lead very nicely into a major topic, which is factoring, and in particular, factoring trinomials is what we'll tackle on Wednesday. So that's what's coming. But also tomorrow is a special day here at GCC. It is advising day. So there are no day classes tomorrow. However, evening classes meet as scheduled. So if you have a Tuesday night class, you go to it tomorrow night. But during the day, hopefully you make an appointment to meet with your academic advisor, talk about coming up with a plan for a course load for you for next semester. So that's what tomorrow is about. Any questions on the schedule? Okay, and then just a quick check here. The next quest is on April the 7th, which when is that? Is that a week from today? I think a week from today is our next quest. April 7th is Monday. Okay, so that's what's on the horizon. And again, we start here on page 23 towards the bottom. Like I mentioned, today we're going to simplify certain types of radicals that we'll be working with in future classes, and then dip our toes into the concept of factoring quadratic trinomials. So number 2 says, let's review how to simplify this radical together, square root of 162. So is 162 a nice number inside of a square root? If you don't know your perfect squares very well, they're up here in yellow. You're just looking to see if 162 is in that bottom row. Is it? No. So so this isn't going to be just a clean single like integer number, but we can simplify it. And the way that we simplify it is to factor it, is to write 162 as the product of two numbers, one of which is nice. So instead of just thinking, do random numbers go into 162, like does 2 go into 162, or does 3 go into 162? The only numbers we care about are, again, these yellow ones. So we're going through this list and asking ourselves if these numbers in yellow go into 162. Does 4 go into 162? And a calculator can help you here if you're not really quick with your division. Does 4 go into 162? So it turns out it doesn't, because 4 goes into 160. And this is 2 more than that. Does 9 go into 162? There's a trick to know whether or not 9 goes into any number. Do you guys know it? Yeah, you add the digits, 1 plus 6 plus 2, which is a really strange thing to do to these digits. What do you get? You get 9. And if the sum is divisible by 9, then so is the number. Super. So 9 goes evenly into this number. So let's factor it out. So this equals square root of 9 times something. So again, if you have a calculator, great. Otherwise, you're doing some long division. How many times does 9 go into 162? 18 is right. So 162 is 9 times 18. And then we'll split this up into 2 radicals, because radicals work really nicely over products. And then the square root of 9 comes outside as 3. And so we get 3 square root of 18. Questions on that one? Okay, so is this as simplified as it can be? The answer is no, because we still have 18, and 18 is not in our lists, but there is a number in our list that goes into 18, and if there's a number that goes in, you got to keep going. What nice number goes into 18? It's 9, so we've got to do this again. So this equals 3 square root of, and then instead of 18, we're writing 9 times how much? 2. And then split it up just like before. And just like before, square root of 9 comes outside as 3, square root of 2. Now I've left a space here. What symbol goes in that space? It's times. This is all multiplication. Everything you see up here is multiplication, right? It's 3 times the square root of 18. Times, 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 and then times. So then our final answer in this case is 9 square root of 2. Done. All right, Alan is trying to save us some time. So let's look at the better way to do this. We stopped at 9 because 9 went into 162, and we were quite happy about that. But let's be greedy and just see if there's anything bigger than 9 that goes into 162. Okay, so does 16 go into 162? You can check on your calculator. If 4 doesn't go in, then 16 certainly doesn't go in. Does 25 go into 162? No chance. Does 36 go into 162? That's not as obvious. It turns out it doesn't. 49, 64, finally get to 81. 81 goes into 162. So better is to say 162 is really 81 times how much? 2. So be greedy if possible. Don't stop with the smallest number that works. See if there's something bigger. 81 comes outside as 9, and then square root of 2 is inside. Same answer? Okay. So we'll get it right either way, but clearly finding the biggest number is in our best interest. Questions on this? Okay, so we've done this before. That was just a quick review. Let's take a look at number 3. Let's go to Lauren. Can you read 3? Raise your hand if you've seen the beautiful quadratic formula before. You all just agree that it's beautiful by raising your hand right there. See how I got you? So we're going to use this soon enough, but before we use it, before we have it in the context of solving quadratic equations, whatever those are, we're gonna need to work on simplifying such things because the square root appears in here, and we've spent the last couple of days thinking about square roots. So this is a good time to see the square root in action in the middle of some bigger thing, this quadratic formula. And so here's an example of how to reduce something that came out of the quadratic formula. So suppose that you just had in front of you this crazy looking thing, negative 16 plus or minus the square root of 128 over 8, and we want to clean that up. We want to simplify it. Okay, so the only thing we can do at the start is think about that 128, and it's a square root problem, just like the 162. So again, we're looking for yellow numbers that go perfectly into 128. I've done the work for you here. 64, which is yellow, goes into 128 twice, right? And then what does that 64 come out as? 8. So there's our 8 root 2 sitting over here, right? That 64 came outside as an 8. And then we're going to, so there's nothing new there. This is just a square root embedded in something more complicated. But the new part is that we're going to end up wanting to split up these complicated looking things into 2 fractions. And it's a really strange thing to see, but it's something you guys all believe to be true. What if I gave you this? 3 over 4 plus 2 over 4. What is that equal to? It's 5/4, right? Yeah. But I'm going to write it like this, which is what you did in your head, but you just did it so quickly you didn't even think about this being what you did, right? They're equal. Okay, so you're really used to going that direction, combining 2 fractions that have the same denominator. Okay, well, it turns out you can uncombine if you're ever interested in doing so, right? It's the same thing, just going backwards. So if you see 2 numbers added together on top of one single number down here, you can take that number and put it underneath both, right? 4 is under the 3, the 4 is under the 2, the plus sign is right in the middle. So that's the direction we're going in here. There's the plus or minus that we're going to split over. And so we get this piece right here, 16 over 8 with a negative is right there. We see it? And then the other piece is this guy, 8 root 2 over 8, which is there. And then the plus or minus just got copied in the middle. Buy it? This is the new thing. And now that we have 2 simpler looking fractions, we can just reduce them separately. How much is negative 16 over 8? Negative 2. There it is. And what cancels in this fraction? 8s. 8s cancel, and you're just left with root 2. Could I cancel the 2 and the 8 and make a 4 down here? No. Anything inside a radical does not combine with anything outside a radical. So these guys are not combinable. The only reason we can cancel these is because they're both outside. All right? So the goal, the new thing for here, is to take a complicated looking thing like that and get it over to this guy, which you'll agree is less complicated, and we call this simplified. Okay, so let's go to the next page. Number 4, we'll go to Victor. Read number 4, please. Okay, so this is completely separate from what we were doing before. But we're going to multiply these two things together, x plus 2 times x plus 3. And first thing I'll say is some vocabulary. How many terms are in each of these? 2. And so the fancy math word for something with 2 terms, the distribution is what we're going to do to these guys. But binomial, that's what these things are. Bi meaning 2. So we have 2 binomials getting multiplied together. And when we have 2 binomials getting multiplied together, there are a couple of different ways that we can handle it. And so one of them is something that you saw with either me or Sandy, if you took 095 with either of us. But it's the lobster claw method. You guys see like a lobster claw there? And what we're going to do with these little lines or curves that I've drawn is just multiply everything that I've connected with curves. And I've connected the first x with both the things in the second parentheses, and then I connected the 2 with both the things in the second parentheses. And so we're going to multiply. So let's multiply, I'll do this one here, multiply these 2 guys together. What do we get? X squared. And then we'll multiply these guys here. 3x, just x times 3, but writing it the other order. And then I'll multiply these 2 here, 2x, and then finally I'll multiply these guys here, 6. Everybody see the 4 things from the lobster claw? We're multiplying 4 pairs of things together. And I've left spaces in between. What goes in the spaces? It's all plus signs. These are all addition things. So you multiply and then you add the results, keeping in mind that some of those results might be negative, and I'd probably just write that as subtraction. So we'll see that in the very next one. And so we'll combine the terms in the middle, x squared plus 5x plus 6. And there isn't anything else we can do with that. Those 3 terms are not like terms. So that's the lobster claw method. Just as good, you could use something called the box method. So we'll give you an or. Okay, so we're going to draw a square, and then we're going to draw 2 lines in the middle of the square. And at the top of the square, we're going to put the x plus 2. So x here, and then plus 2 there. And then on the left side of the square, we're going to put the x and then the plus 3. And here's what we do. We're going to take this guy right here, and we're going to multiply it by this guy right here, and we're going to put the answer in that box. X times x is x squared. And next thing I'm going to do is multiply that same guy by this guy over here and put the answer in the top right box. And what do we get there? 2x. And then we play the same game in the bottom row. So this positive 3 is going to get multiplied by that guy, and we get 3x. And then the last one is the positive 3 multiplied by that positive 2, and we get 6. And then we'll just write our answer. So that whole thing means x squared plus 2x plus 3x plus 6, just adding up all 4 things in the boxes. And again, we'll combine the terms in the middle. So that's the same 5x we got before. Raise your hand if you've seen the box method for multiplying. About half of us, maybe. Do we see that they're the same, like the box and the lobster claw? They both say, in plain English, multiply everything in the first parentheses by everything in the second parentheses. Just two different ways to display that. Okay, there is a third way to multiply two binomials together. And in fact, it's probably the most common way this is taught in high school. It's an acronym with 4 letters. Victor. Victor says FOIL. Raise your hand if you've foiled before. Sorry to hear that. FOIL. All right, what does FOIL stand for? FOIL. Handy little acronym. First, outer, inner, last. All right, we'll play the highlighting game real quick. Okay, if I'm looking back at the original, x plus 2 times x plus 3, what's the first term in the first parentheses? Is this x? What's the first term in the second parentheses? Also x, and so that would say we multiply the two x's together. So in this case, it would just be the x times x, or x squared. Okay, the next one we'll do is the outers. Outers meaning the things that are farthest from the middle of this whole big expression. So that and that are the outers, right? The things that are on the outside. So x and 3, x times 3 gives me 3x. Continuing on, next one are the inners. Which ones are the two inners? It's the 2 and the x, things that aren't the outers. They're near the middle, so we're multiplying 2 and x together. 2 times x, which is just 2x. And then finally, what are the lasts? See that? The last thing in the first parentheses is 2. Last thing in the second parentheses is 3. So again, we multiply 2 times 3. And again, we get 6. Same, exactly the same. Just another way to write it. Okay, so FOIL. FOIL, like I said, is probably the most common way this is taught. I'm not a fan of FOIL. I'm going to try to avoid using the word FOIL ever again in this class because the lobster claw method works even if you have a binomial times a trinomial. So if I wanted to, I'm not going to do this right now, but if I wanted to multiply these two together, I would do this x times everybody, and then I would do this 2 times everybody. We got like a double claw thing happening, some kind of mutant lobster. And the lobster claw method is fine. I'm going to erase this in a second, but it'll be a mess in the beginning. What am I doing? X squared plus 3x plus 6. So if I extend my rectangle down here, and I just make this a 3x and this a 6, then I can just draw a few more sets of arrows in the natural places, and the box method will get me the right answer. But FOIL only works if it happens to be 2 terms times 2 terms. And it's completely useless for anything else. So just stick a third term in one of these parentheses, FOIL is out the window. So I'd much rather learn the thing that generalizes, either the lobster claw or the box, than FOIL, which is only good in one specific case. Okay, let's get rid of some of this stuff. All right, let's come down here and try part B. So actually, B, C, and D. See if you guys can do those with your neighbors. Either lobster claw or box, preferably not FOIL. And check your answers with your neighbors. Okay, so we got our answers to the 3, x squared minus 5x plus 6, x squared plus x minus 6, and x squared minus x minus 6. And now let's take a look at 5. Morgan, could you read 5? Okay, so let's give this a shot. So what was exactly the same in the parentheses for all 4 problems? Were the numbers exactly the same? What do you mean? Yeah, the signs are different. So I'm going to say these numbers change. Sometimes it's +2 and sometimes it's -2. But what's the same all the time? Is the x, right? The first thing in every parentheses is just plain old x. So we can ignore that x because it's the same all the way through and really just focus on the numbers. The first one is a +2 and a +3. The next one is a -2 and a -3, and so on. All right, so we're just looking at the numbers. Okay, now let's go ahead and compare our answers. So maybe I can highlight some of these guys here. So that was one answer, second one, third one. I think we can get them all on the screen here. Okay. What's the same in all four of these answers? X squared. Okay, so we all start with x squared. But then there's some differences, right? The first one, the middle term is a +5x, and the next one is a -5x. Okay, it seems like there's something there. But in the next one, it's a +1x, which is completely different from the 5s that we had. And down here, it's a -1x. So there's something going on with that middle part. But the last part, the last number, the number without x, +6, +6, -6, -6. Okay, there seems like there's an easy pattern here. We just have to figure out why were they all 6s, and how could I tell whether it's going to be +6 or -6? Looking at, and here we'll highlight the numbers, +2, +3, -2, -3, -2, +3, +2, -3. Looking at those yellow numbers and whether you get 6 or -6, is there an easy way to know? Looking at just yellow, is there an easy way to know whether you'll get 6 or -6? Yeah, it just depends on the signs. And if we multiply in part A, the two yellow numbers, what do we get? +6. In part B, what do we get when we multiply the two yellow numbers? Still +6. In part C, -6. And in part D, -6. So do you buy that that last number, the one that has no x's, is just going to be the product of whatever the two numbers are? And it makes sense if you think about it, whether you lobster claw or box method or FOIL, if you so choose, at some point you are multiplying these two numbers together. Okay, so I think I'm happy to say something like, let's see, so the resulting products and describe the patterns. All right, so I don't quite have a good way to write this actually. So let's suppose that we're multiplying x plus something times x plus something else. And so what we end up doing is taking the product of these two numbers and saying it goes at the end of the answer. By that, multiply those two numbers, that's the thing that gets shoved at the end. Could be +6, could be -6, could be something else if the numbers were different. But it seemed like that was the pattern. Those two numbers get multiplied and go at the end. Okay, now the harder part of the pattern. I want some easy rule that's going to tell me what I can do with the two highlighted numbers in order to get the thing in the middle. First one, it was 5x, positive. Second one, it was -5x. Third one, it was +1x. And the fourth one was -1x. There's something we can do with those yellow pairs of numbers to get the guy in the middle. Let's just look at the first row. What can you do with the +2 and +3 to get this +5x? Can't we just add 2 and 3? Add 2 and 3, you get the 5, and there's an x tacked on at the end. Okay, what do you get if you add the -2 and the -3? -5, is that the thing that had the x on it? It is. Well, this is promising. What do you get if you add these next two numbers in yellow? It's +1, right? Is that what was in front of the x? It is. And if we add these last two numbers, -1, was that the thing in front of the x? It was. And so it turns out that, yeah, you just end up adding the two numbers and putting it in the middle with an X on it. Does it make sense? Sure it does. When we did our lobster claw, one thing we ended up with was a X times 3, and another thing we ended up with was X times 2. Or here in the box method, that was our 2X and our 3X. And what do you get when you add those up? 5X, but couldn't we just add the 2? I mean, you just added the 2 and the 3 and you tacked an X on at the end because they both had X. So it's perfectly reasonable to say, oh sure, we'll just add up these two numbers with an X at the end. So I think we can say that as well. It's the same two numbers. We'll change colors here. Here and here. The sum goes in the middle of the answer with what tacked on? What did each of the middle guys have at an X? So with an X tacked on. Okay. Multiplying two binomials, not hard, just practice a little bit and it becomes straightforward. But going the other direction is much tougher. So what do I mean by when I say going the other direction? So I'm just going to temporarily cross something off here. Sky. Just don't look at that. But suppose I give you x squared plus 4x plus 3. And I say some mean person took two binomials, multiplied them together, and simplified, and this was the answer, x squared plus 4x plus 3. And this mean person wants us to figure out what they started with. So we're looking for two binomials that multiply and give me x squared plus 4x plus 3. Okay, so the answer is sitting right there, but like I said, let's see if we can ignore it. In all of the examples above, what was the first thing in both parentheses? X. So it seems reasonable that an X and an X will start the ball rolling. And by the way, when I multiply them, what will I get? The X squared. So that's how we build the X squared. It's the only way we're going to build the X squared. Okay, but now we're looking for the patterns that we just established here. So the patterns say the product of these two blank numbers, the two missing numbers in the parentheses, product goes at the end of the answer. So in part A, what's the product of these two blank numbers supposed to be? It's supposed to be that positive 3, right? Because that's the thing at the end. So what we want, I'll write it in purple, product of two numbers, I don't know what the numbers are yet, is, I'm going to really highlight the fact that it's a positive 3. That's what we're after. Product of two numbers is positive 3. And then reading this part in green, we said that, okay, but if you add those same two numbers, you get the thing that's in the middle of the answer that has an X tacked onto it. So if I add the two missing numbers, what am I supposed to get? I'm supposed to get the 4. Add up those two numbers and you get the thing in the middle, 4, with the X tacked on. So we'll write this in green here. The sum of those same two unknown numbers is, and I'll highlight the positiveness of this number 4. Okay, so that's the mystery we have to solve. Find two numbers whose product is positive 3 and whose sum is positive 4. Can anybody find two such numbers? 3 and 1. Right. And this one's not too hard because there aren't many numbers whose product is 3. There aren't many integers whose product is 3. So 3 and 1 is one possibility. Are there any two other integers whose product is positive 3? Negative 3 and negative 1. So really there were two different possibilities to consider, but we wanted the one whose sum was positive 4. Okay, that's plus 1 and plus 3. And so that will be our answer. Victor. Makes no difference which one goes first. You could write the 3 in the first one and the 1 at the end. It doesn't matter. It's the same as saying, 4 times 2 is exactly the same as 2 times 4. That's true, isn't it? So if you choose to take this whole thing and swap it with that whole thing, no problem. You're multiplying 2 numbers and the order makes no difference. So it doesn't matter which one goes where. Soon enough, we're going to see more complicated ones where one of them has like a 2 in the front of it, then it makes a difference. Because swapping the 1 and the 3 isn't the same as changing the whole big things. You can change the whole big things. There we'll have to be a little bit more careful, but that's not for a couple of classes. Okay, so I think that's that. X plus 3, x plus 1 in some order is our answer. And that right there is called factoring. You took something right here that was a sum, and you turned it into something which was a product. And isn't that what it means to factor? Like if I say factor the number 9, how do you factor 9? 3 times 3, right? You turn 9 into a product. That's what factor means, turn the thing into a product. So we turned this, which was a sum, into a product. Okay, so the group work is here. There are 3 other parts of this guy. And then on the next page, it's some more stuff with square roots. Now, we have like 35 minutes left. You will finish this in much less than 35 minutes. So when you finish, go back to some recent class, could be last class or 2 classes ago, something that is still shaky for you, and fill in those gaps and ask questions of your neighbors and ask questions of me. Again, this is easier than some of the stuff we've just come through. So let's use the extra time that we have to work on the stuff that was tougher. And we may end up spending like the last 10 or 15 minutes of today just getting a sneak peek of next class. We'll see. So go ahead and see how fast you can get through these, and then we'll come together in a little bit.